Thanks everyone for coming. This is a joint research project with Nicole, Immorlica from Microsoft, and my advisor, Rob Townsend. So data is becoming increasingly available and better processed. So in financial markets, this in particular has brought the hope that the doors of financial access will open for some of the people who need the most, like the people for which banks have previously had very short financial histories and could not reach with financial products. However, if the reason why those markets are not working is adverse selection or is an imperfect information problem, then it's not going to be the case that more information is going to necessarily increase the volume of transactions or the gains from trade from those transactions. And since that's the case, what we want to ask in this paper is, how can we design data sharing protocols that guarantee that that the volume of transactions or the quality-weighted volume of transactions always improve, so that borrowers are, on average, they're better off when more information gets reviewed in the market. So to answer this question, what we're going to do is solve an information design problem, or the optimal disclosure problem of a partially informed intermediary that has access to a rich data set and wants to choose what features of that data set to review to potential investors in a way that maximizes the probability of successful transactions weighted by the size of gains from trade. We're going to derive an optimal disclosure system, and we're going to show that this optimal disclosure system, in general, needs to satisfy three simple rules of thumb that can be written in terms of sufficient statistics that can be estimated in the data. And then we're going to apply our results to the rural credit markets in Thailand. We think this is a particularly fitting setup because on one hand, there's a fee informal segment. And on the other hand, we benefit from extensive data from the Townsend Thai Project that includes balance sheets, income statements, and credit histories of those farmers. So the size of the gains from trade are potentially large because there's a fee informal segment. And we have a lot of data that Rob has collected for more than 10 years in Thailand. So let's jump right into the model. And so there are going to be types, which are borrowers' private information. And we're going to denote those types omega. The borrowers are going to sell a $1 claim to be paid in the future. And the investors, we're going to denote the value for the investors for that $1 claim as A of omega. So A of omega, you can think of the probability of repayment for the investor. And the value for the borrower, we're going to denote B of omega. And then we can think of that additionally incorporating an implicit insurance value. So that the borrower may not pay the loan back precisely at the moment where money is very valuable for the borrower. So those values do not need to be the same. And that's the reason why there are financial markets to start with. And the platform will have access to signal realizations, Z of omega. So those signals are informative about the reservation value for borrowers and the probabilities of repayment, the credit worthiness of those borrowers. And the platform will commit to information disclosure policy. And then after seeing a realization of the signal, we'll review a message, M of omega, and pass this message to the investors. There's going to be competition among the investors, so prices are going to be the average value for the investor. And if there are multiple prices, there's a little bit of technical condition. If there's multiple prices that the investors would make investors break even, we're going to pick the highest among them. Otherwise, there's a deviation from a potential investor around that higher price that would generate positive profits and attract all the borrowers. So there are borrowers, investors, and a platform. The borrowers, the platform sees signals from the borrowers, commits to information disclosure policy, send messages to the investors, and then borrowers and investors interact with those lending contracts that the investors are going to be competing to offer to the borrowers. So what is this information disclosure policy, or disclosure problem? In general, we can think of a platform picking a message space and then picking a conditional distribution of messages given those signals, subject to that constraint that the equilibrium is described by this Lemons type of equation, that investors break even. However, this problem is a bit complicated, but it can be simplified by noticing two facts. First, we found loss messages can be identified by their equilibrium prices. If there are two prices, two messages, such that the investors break even at that price, without loss, the platform can combine those two messages into the same message, and nothing will change. And second, welfare is increasing prices for the borrowers, and because the platform is maximizing the welfare of the borrowers, we can drop this supremo. The platform is already picking the highest price. And this allows us to simplify this problem and write in terms of conditional distributions of signals and prices. And so when we write this problem as the platform picking a conditional distribution of prices given the signals, this is a standard linear programming problem. So here, the platform maximizes this conditional distribution, but to maximize the borrower surplus, subject to the constraint that for the bundle that is assigned to the same price must be such that the investors are breaking even. So having formulated this problem, we can use tools from linear programming to characterize simple properties that solutions to this problem should satisfy. In particular, if you think of a policy, a candidate policy, and that candidate policy is optimal, we can think of bundling together two signals two messages that are originally separated. And when we do that and combine those two messages into the right proportion, such as that the new message would make the investors break even, that's if that original policy, candidate policy, is optimal, that should not increase the welfare for the planner, and so therefore this set of inequalities must be satisfied. And there are some special cases where that's the only kind of policy that you can do, and in that case, this condition is not only necessary but sufficient. So if you start from full disclosure policy, the only thing that you can do is combine two different signals, and anything else that you can do can be written as a bunch of different combinations that you combine together. So more interesting, perhaps, is like we can specialize to a case where those bundles have prices that are nearby to each other, and write those conditions in terms of ingredients that are more familiar from an economic perspective, like prices and elasticities. So when we do that, we were going to conclude that under any optimal policy, prices and elasticities need to satisfy a simple relationship. Whenever two markets have higher prices, they must have, whenever a market Z has a higher price than the market Z prime, it also must be the case that the elasticity of the value for the investors with respect to the price is higher at the market Z than at the market Z prime. Perhaps I can show you a figure to illustrate why that's the case. So in this figure, I'm plotting prices and the average value for the investors. So whenever prices crosses the 45-degree line, the dashed line, so then whenever the average value crosses the 45-degree line, that's an equilibrium point. That's a point where the investors are break even. And here we have the two signals Z and Z prime, and we are plotting their equilibrium prices under full disclosure. So then we can think what would happen if we combine those two signals, Z and Z prime, into another bundle, and then ask whether that would increase welfare for the borrowers. So if we do that, whenever we pick a unit of Z and lower its price, the investors are going to be making a profit of the size of the blue segment. That's the difference between the average value for the investors and the 45-degree line. And for each unit of Z prime, the investors are going to be making a loss of the size of the red segment. That's the difference between the 45-degree line and the average value for Z prime. So if the investors break even at this price, the quantities of Z and Z prime that we put together must be inversely proportional to the size of those segments. And we're going to pick fewer units of Z relative to the number of units of Z prime in that bundle. That means that we are going to be raising the price of more units than the number of units that we are lowering the price. And because under our measure of welfare, we don't care about who are the borrowers that we are lowering the price and relative to the borrowers that we are raising the prices, that's going to be good for the planner, good for the size of gains from trade in this market. So we can do the same thing when the slopes are switched, and we're going to conclude that that would not increase welfare. And we can do the analogous thing by starting from, instead of, let's consider different messages and pack them together. Let's pick a message that combines different signals, and let's unpack that bundle and see what's the difference in welfare that we would generate. And when we combine that, when we do that, we're going to arrive at analogous expressions that are more complicated. But when we specialize to the case, we're going to find, surprisingly, that at any bundle, the signals that are assigned to that bundle, they need to satisfy a fine relationship between markups and the elasticity of profits for the investor. And that means in practice that few signals should be pulled together. When they're if you pick more than 2 signals, if you pick 3 arbitrary signals, it's not going to be the case that those 3 signals are going to lie on that affine relationship. So if you have a finite number of signals, at most 2 signals should be pulled together at any bundle. So those rules of thumb can be illustrated in the following example. So here I'm plotting elasticity of the expected value with respect to price as a function of prices. And we have a full disclosure policy. That's the red dots. And we have the optimal policy that the platform would pick in this case. And we can see that there is an increasing relationship under the optimal policy between the elasticity of the expected value and the prices. And whenever 2 signals are combined into the same message, it's the case that is a high price and low elasticity signal that is combined with a low price and high elasticity. And in general, at most 2 signals are combined in each bundle. So now let's switch gears and move to the empirical application. So we're going to use this Thai Townsend monthly data set that follows farmers in Thailand for a period of more than 13 years in 16 different villages, and includes detailed information on their consumption, income, and crops, livestock, the balance sheets, the cash flows, and their credit histories. And we're going to assume that the platform has access to those variables and that the investors do not. And we're going to ask the question, what would be the optimal information policy for the platform that's interested in maximizing the gains from trade, the borrower surplus in that market? So we also going to rely on an identification strategy that leverages the fact that in that market, there's a key player. There's the Bank of Agriculture and agricultural cooperatives. And we're going to use machine learning methods, causal forests, to estimate slopes of supply and demand that tells us what is the joint distribution of values for the borrowers and investors. And we're going to assume that those changes in interest rate from this agricultural bank, because those are infrequently updated and are as good as random conditional on the set of observables we have in the data set. So when we do that, we can, after recovering a joint distribution of values for the platform, for the borrowers and for the investors, we can calculate what would be the outcome under the optimal policy and under the full disclosure policy. And we're going to see that even out of sample, with like splitting the sample between a validation sample and a test sample, we find that there is substantial gains from trade from moving from full disclosure to the optimal disclosure policy of the order of 5% of their the monthly income. And moreover, the variables that the optimal policy uses, it looks like they're more about the solvency of the farmers than the liquidity, the liquidity of the farmers, that would feature standard credit scores that care only about the credit worthiness of those borrowers. So to conclude, we computed and show what is the information disclosure policy looks like. And we established several general properties of those policies, those optimal policies. We presented a framework to estimate those statistics that matter for evaluating those policies and for producing optimal credit scores. And we showed that there's meaningful gains from implementing this optimal information disclosure policy.
Thanks for the talk. This is more of a clarification question. I think I missed it. In the empirical example, can you maybe describe how you sort of like how you simulate or identified the sort of their counterfactual behavior under the different policy?
Yeah, so the idea is that we observe those borrowers under different interest rates because this government-owned bank has infrequently updated those rules of interest rates that they use to those borrowers. So we can use those changes in the policy as a source of identification for those slopes of supply and demand, and those slopes of supply and demand are what tells us what will be their behavior under different policies.
Thank you.
If there are no additional questions, let's thank our speaker again. And